Let's apply what we know about fluids in hydrostatic equilibrium to a series of examples. There will be points when I ask you to pause the video and work something out for yourself, so be ready for that. All right, first example, we've got a set of cylinders here filled or partially filled with water, all connected here below, so it's one single fluid. And these 5 cylinders are all open to the air, but this last one here has a sealed cap on it right there. And we might ask, what is the net force due to pressure on that sealed cap? So to answer that, we'll use the idea that pressure is the same along any horizontal line in a single fluid. So if we draw this horizontal line across the system, touching points J and K, we can note that the pressures at those 2 points must be the same. So we'll work out the pressure here at K just underneath the cap, the water pressure underneath the cap, by working out the pressure over here at J, and we'll know that they are the same. And so the pressure here at J, we can work out by knowing that it is 2 meters deep into the water. So the pressure at K equals the pressure at J. The pressure at J equals the atmospheric pressure above plus this rho g d term, where d is the depth of 2 meters. So put in the density of water and little g and 2 meter depth, and we get a 0.2 atmosphere increase in pressure when we are 2 meters deep into the water. So at point J, the pressure is 1.2 atmospheres. Therefore, the pressure here at point K is also 1.2 atmospheres. So for our cap here that is sealing this pipe, there is an upward pressure from the water of 1.2 atmospheres and a force downward due to the air pressure above, which is 1 atmosphere. So the net force on that cap due to pressure will be the upward force from the water pressure minus the downward force from the air pressure. Upward force over, and here the A here, that's the area of the cap. So we'll factor out that A, and then we just need the difference between the water pressure and the air pressure. It's a difference of 0.2 atmospheres, or 0.2 times 10 to the 5th pascals. That times 1 square meter cross-sectional area of that cap. And a pascal times a meter squared is a newton, so that then is 2 times 10 to the 4th newtons, 20,000 newtons of force upwards pushing on that cap as this water tries to burst out of the pipe here. Which means you would have to apply a force of 20,000 newtons downward just to hold this cap in place. If the cap were 2 tons, then it could hold itself down with its own weight, but otherwise you need a construction capable of providing the equivalent of 2 tons of force just to keep that pipe from bursting there. Well, what we're not going to do is make the situation even more dramatic by loading up those 4 columns with 4 unknown weights on light piston heads without trapping any air in between. And so these will be our 4 weights, A, B, C, and D, sitting on piston heads with the cross-sectional areas 2 meters squared for these 2 and 1 meter squared for those. We're going to load those weights into these 4 columns and just have a more 3-dimensional picture of what this is going to look like. Let's say this is our set of pipes here, and they are each rectangular or square columns with the width going into the page, a delta y, let's say, of 1 meter. So this is then 1 square meter cap here, and then a 1 by 2, so 2 square meter cap there. So loading the water in, loading these weights in, making a tight seal, we're going to press the water down, and since water, a liquid, is incompressible, the total volume of water will have to be the same. So as we displace water in these columns, the water is going to have to rise up through this column here, all of which is going to increase the pressure on our sealed cap over there. So suppose we load in those pistons and we see this happen. Mass A basically doesn't move the water at all. It's going to rest right at that original height of 4 meters. Mass B is going to press the water down a meter, C presses down 2 meters, and D presses down 3 meters here. All that displaced water rises up the column here to a new maximum height there at 11 meters. And now we've got an increased pressure over here at our cap. So from looking at this picture, can you rank and determine these masses? Maybe just take a moment to see if you can qualitatively rank them. That is, can you tell which of these masses is the biggest, which is the smallest? Are any of them the same? Are they all the same? Take a moment to consider that question. And if you have a thought in mind about the relative masses here, let's now do some calculations. Let's first compute the water pressure just under each piston head. So the water pressure just under piston A, just under piston B, just under piston C, and just under piston D. Pause the video and use what you know to work out what the pressures are, the water pressures are at those 4 points. All set? All right. What you can do to work out those pressures is use our principle that pressure stays the same along any horizontal line in a fluid. So the pressure here at point A will be the same as the pressure in this column here at a height of 4 meters above the ground. The pressure at B will be the same as the pressure in this column on the left at 3 meters up. Pressure at C will be the same as the pressure in that column on the left at 2 meters up, and pressure at D will be the same as the pressure in this column at 1 meter above the bottom. So if we can compute the pressures here, 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 and here, then we know the pressures just underneath each of those pistons. So at point A, the water pressure is the same as the pressure at a Z value of 4 meters. And at 4 meters, the pressure here will be equal to the atmospheric pressure plus rho GD for this depth. So we're at a depth of 7 meters there at this position. B will be at a depth of 8 meters, C is at a depth of 9 meters, and D is at a depth of 10 meters. So we therefore compute the water pressures at those 4 points by setting them equal to the pressures at these 4 points in that leftmost column, each equal to the atmospheric pressure plus rho GD, so 1 atm plus the density of water times little g times the depth of those 4 points. Getting us at piston A, 1.7 atmospheres, B, 1.8 atmospheres, and so on. Note here, the pressure at A has increased even though the water is still at the same height as before. The new pressure under A is 1.7 atmospheres. 1.7 atmospheres here compared to the beginning, where the pressure at that same point was just 1 atmosphere, matching the gas up above. So the pressure here at A has increased, even though the water didn't change its level here, because this water over here rose up that column. So this pressure is now 1.7 atmospheres, then here 1.8, 1.9, and 2.0 full atmospheres down there at D. So now that we know the pressure underneath each of those pistons, you're going to pause the video again and work out the following. Sum the forces on each weight piston system. Include gravity and the forces from the water below and the air above, but you can neglect friction between the piston heads and the column walls. Use that to then compute each mass, and we'll have our ranking. So pause the video and work that out for yourself. All set? Okay, here are those sums. Net force should be 0 on each of those pistons. Upward force of water, downward force from the air, downward force of gravity, rearrange to get Fg by itself, and it'll be equal to the upward force of water minus the downward force from the air. So pressure of the water times the cross-sectional area minus the pressure from the air times the cross-sectional area. Factor out the cross-sectional areas and we get the pressure difference So the water is 1.7 atmospheres, air is 1 atmosphere. So there's a pressure difference of 0.7 atmospheres times the cross-sectional area gives you this many newtons. Divide that by little g to find our mass. So A, 14,000 kilograms, and these values for B, C, and D. Note that 1,000 kilograms, that's about 1 ton, 2,200 pounds, a little bit more than a ton actually. So this is a 14-ton mass here and a 10-ton mass there, and we see our rankings. The most massive is in fact B, more massive than A, more massive than D, and the least of them is C. So the mass is not the only factor here that determines how deep the piston is going to go. The cross-sectional area matters as well. The pressure provided by the piston is the force per unit area. So B can be the biggest mass, but that weight is spread out over a bigger surface area than, say, C's weight is. So it provides less pressure than C, even though C is a bigger weight than even though C is a smaller weight than B. Okay, so with that result, we can now ask about the net force due to pressure on the sealed cap now. With this column of water all the way up here, what's the new pressure right there? So we would note that the pressure, the water pressure just underneath that cap will be the same as the water pressure just underneath C, same as the water pressure over here at 0.2, at 2 meters above the bottom. So the water pressure is the same as the pressure at Z equals 2, so that's 1.9 atmospheres. So the upward force of water on the cap minus the downward force from air on the cap gives us this difference in pressure, 0.9 ATMs, times the 1 square meter area of that cap is 90,000 newtons, equivalent to now a 10-ton cap being needed to prevent the water from bursting out of this high-pressure pipe at this point. 10 tons being also the weight of C. So if we need a 10-ton mass here to press the water down that far, then we would also need a 10-ton mass sitting right there. And if you don't have a 10-ton mass here, then you just need a construction capable of providing that much downward force to seal this very highly pressurized pipe right there.